All right, come back to me. 3, 2, 1. I'm going to point to a table. You guys holler, okay? Give me an example of Kendall's table.
Hot air balloon.
Hot air balloons. Who's ever ridden on a hot air balloon? Oh, you guys are so spoiled. My husband won't take me. I'm going to force him to take me for like an anniversary. Okay, I want to go on a hot air balloon, but that's just the premise of hot air rises because density of gas is lower under high temperatures. Maverick's table.
Greenhouse gases?
Say again?
Greenhouse gases?
Greenhouse gases, and why are those important? Some of your table, what's a greenhouse gas? What's it do? We just had an assignment on that last week. It causes the temperature of our atmosphere to rise because of their hold on to infrared radiation. Not good. Andrew's table. What about it? Okay, so just grills. What's the most important thing you think of? No, it's energy producing gas, right? So we're going to take propane, we're going to combust it, produce energy, which is useful in a lot of ways. ST table?
Atmosphere
What about it?
has gases in it
Yeah, why is it important?
because
We breathe, and our lungs function based on pressure differences. So we breathe in. Deep breath, come on, deep breath. Okay, what's happening on the inside of your lungs right now?
expanding
Why is it expanding?
because they're taking it in.
Okay, because you're taking in more moles of gas or more grams or more whatever particles of gas, and then expands, and then and then the pressure therefore decreases, well, the pressure changes, I won't say decreases. Pressure changes and the volume changes as well. Front table up here.
Cooking.
Cooking, what about cooking?
Like if you have a gas stove, then you need to have
When you say gas stove, what are you actually speaking of? Some sort of hydrocarbon, right? Where it might be propane, maybe, and so a lot of people have gas. Like our gas jets have a mixture of propane and natural gas, like methane, a couple of other combustible gases. But where else in baking is our gas is important? What about the other one? Okay, so the heat itself will cause decomposition of some sort of sodium bicarbonate, baking soda, and it causes carbon dioxide to be formed, which is the gas that causes things to rise. I've missed a table. Back table? What about, those aren't gases. Okay, do they? Which one, which one? Come on, table. Right, Deflategate, guys, come on. That was a big deal. We have to know about gases in football to make sure they're not cheating. Also, you're talking about exchange of gases in photosynthesis and cellular respiration. Obviously very important. Nobody said birthday balloons. I'm a little sad. Okay. I know, it's good. All right, so this is kind of the big slide for today. I'm going to be quiet. These are 4 variables that you should have in your notes. So I would write down variables used to describe gases, and I have one more down here at the bottom. So this is like in your notes someplace. I would not put this on your Fumble just because your Fumble is going to be full of information. You don't have that kind of space. And honestly, I don't care if you write on the back of your reading guide, but someplace where you're going to find this information. Give yourself to each other. At this point, you are personalizing your education. I am just asking for high expectations. Variables used to discuss or to describe gases. We'll scroll down a little bit to see that last piece, which is moles. Alright, so obviously from the gas laws that you've already seen on your reading guide and these variables here, you're understanding there's a lot of relationships that are going to come into play. Relationships between pressure and volume, pressure and temperature and volume, amount and pressure, amount and volume. Like any of these combinations could be asked of you to describe the relationship between them. But the gas laws, like the Boyle's law, Charles' law, Gay-Lussac's law, they all have the relationships embedded in more of a mathematical sense, but we need to feel comfortable looking at them in a qualitative sense as well. So, for example, box of air. Who's got their box of air? I don't put it on homework. You just got to bring it every day. Okay. You have your box of air. We have a specific volume. Everybody, whip it out. Let's go. It's going to help you. Okay. If you increase the pressure in your box of air, what happens to volume? Okay, hold on. Increase the pressure on box of air. What happened to volume? It got smaller, right? It decreased. So is that a direct or an indirect relationship? So if I increase pressure, volume decreased. If you increase one variable and the other decreases, they can't be directly related because that means they move the same direction. Try again. It must be an indirect relationship or an inverse relationship, meaning that they have an opposite effect upon each other. So that's what we're going to be talking about. Two things I'm going to mention here. We already know the units of pressure. We've mentioned this before. We know how to convert between them. Do we still feel good with that? Do we still feel good with that?
Yes.
Okay, thank you. So I'll ask that if it says to go to a specific unit of pressure, you have to go to that unit of pressure. If not, if it doesn't indicate and it's just like says what's the pressure, any of these pressure units will apply and be fine. Second, we talked about temperature in our heat curve, and I kept saying temperature is related to kinetic energy. It's because what is temperature? The definition. Yeah, it's just literally the average of all the kinetic energy of particles. So if I have a particle of gas that's moving really fast, and a particle of gas that's moving kind of slow, and that's moving kind of medium, then I would have to average all these particles of gases' kinetic energies to get the temperature, but the temperature should reflect the average of all those speeds or those velocities as well. And then in terms of using calculations, using variables like this in calculations, we have to use Kelvin. Now, I'm going to be giving you Celsius all day. I probably will almost never give you Kelvin, but you know how to get from Celsius to Kelvin, so this is very important. Anytime you do a calculation with temperature now with gases, only with gases, we have to use Kelvin, okay? Okay, so let's talk about pressure. Oh, you guys saw the variable for N. N means moles. Okay, so if I say N number, it means moles. Okay, so I thought this was a fun fact. Atmospheric pressure, so like the pressure we are experiencing right now, is roughly equivalent to the force of an elephant balancing on a desk. Does it feel that pressure? Do you feel that pressure? Do you? Just every day, are you just like bogged down and you're like trying to stand up just because the pressure is so bad? No, you don't. You're fine. You're not slumped over on the floor in a puddle. Like, you're fine. Okay? Because what's happening is the atmospheric pressure is equally pressing on you everywhere. It's not just directly down. It's everywhere. So you don't feel it one direction or the other. Unless you're like, climbing a mountain and you're like causing some differences in energy output and pressure. So I'm going to show you guys a quick demonstration of atmospheric pressure. You smell the eggs. Yep, It's not me, it's the eggs. So if you have seen this demonstration, don't spoil my fun. This is one of my favorite ones. So you'll notice I have an egg here. Yes, yes? It does not fit inside the flask. But what we're going to do, we're going to force it into the flask. So we're going to try to do this with 2 hands. I'm going to soak this cotton ball in a little bit of alcohol, and then we'll light it on fire. Okay, so this cotton ball is going to soak it up. And we're going to close the bottle, because, you know, safety and chemicals shouldn't be left open. And I know anticipation is killing you. We're going to light this little guy. You guys saw it does not go in. I'll put that on the table because it's spiky. We're going to light this up. Ooh. Drop. Explain why. Go. Explain your groups why that happened. It's not magic, it's chemistry. Explain why.
I mean, there was a big pressure.
Alright, I want everybody to draw that flask and that egg on their paper. Draw the flask, draw the egg on the paper, and I want you to somehow indicate the chemistry behind what's happening based on your discussions. If you can. Do it in pencil so when you're wrong, you can erase it. Or who feels strongly about what they think happened? Right on this table, what do you guys suggest? It's okay if you're wrong. I'd rather you guys be able to give an indication of what you think, though. Munir, Andrew, done. Let's go. Somebody help me out here.
Basically, when you put the flame in there, it changes the temperature, which then changes the pressure on the bottom to the pressure on the top. You know what I mean?
Okay, hold on. So I'm making baby steps here. So you said as I added the flame, it changed the temperature of the inside here. But what did it change the temperature of? That's the gas particles, right? The gas particles inside. So these gas particles that are hanging out in here, right? Just gas is everywhere. Okay, what did we do when we changed the temperature of them, though?
Increase pressure. Increase the pressure.
One of those, right? Anybody want to take a vote? If I increase the temperature on the particles, what do you think is going to happen? Is it going to decrease pressure? So you got to raise your hand or increase pressure. All right, so you guys are bouncing around, hitting all the corners of the flask. This is just gas particles flying around, hitting things. So you're saying it's increased the pressure inside of the flask. Okay, pick up from there, up front, turntable. If that's, I mean, that's definitely has happened. Absolutely, because we can't avoid temperatures changing particle speeds. Give me another thing you maybe observed, or maybe another thing you thought about. I'll come right back to you. CJ's table. It's something. What did you observe? There's chemistry does not suck. We can't say suck. No, I wanted somebody to say that. Chemistry does not suck. We can't say that. So I've already given you a clue here. I said chemistry does not suck. There's only one other force that could have happened. The volume of what? The volume of this actually would have increased because it's pushing outward, but that egg was in the way and it couldn't get out. So did you guys see it kind of bounce just for a minute? It was just a really small, but it kind of just made a little shimmy. Okay, maybe you didn't. It shimmied. Okay. Anything else you guys can add? Okay, so the gas is moving from an area to another area, and it could be from high concentration, low concentration, because technically, like in this contained vessel, when we combusted, what did we produce through combustion? CO2 and water vapor, right, most likely. So maybe there was more gas in here, and so the gas itself wanted to get out of that high concentration area, so it kind of peeked out the corner where the egg was kind of bouncing. But overall, how did the egg get inside the bottle? The volume down here is increasing.
Yeah.
Where's the volume of the egg? It's not a gas.
Well, but like it's
As the pressure
Okay.
increased, the volume decreased and compressed. So
The egg is not changing volume or pressure, guys. It's just it's a little soft, like you can move it. It's a boiled egg. I heard something here.
actually, when it goes out, it's pushing the egg in, so it's then thinner, so it's not first.
Okay, I'm gonna pick up there. So when some of the gas escaped the corners of where the egg was kind of shimmying around, and then that changed the pressure on the inside. The pressure on the inside went down for a hot second, and then guess what's out here? High. It must have been higher. I won't call it super high because we're not being morphed and shaped and shaped everything. So this is pressure of the atmosphere, and basically the pressure of the atmosphere just pushed the egg right in.
how are you gonna get it out?
How would I get it out? It don't come out. How do I get it out? Say again? Put the fire on the bottom. I just have to get a Bunsen burner and heat this thing up, and it goes boop. I'm not doing that right now. I don't have a Bunsen burner up here. Sorry to kill your dreams there. I have one more for you though. All right, so who's got a birthday in April? Nobody? March? Okay, I didn't ask you. Well, come on, Munir. You said March. All right. I'm just gonna have you do one thing for me. Maybe it's get the candles open. Maybe that's the thing I need you to do. Hold on. Okay, come on this side. You're in the way. All right, so Munir is going to light these birthday candles for our little friend. Our little friend. It's gonna be like this. No, it's not his birthday. There's nobody's birthday. Legit. It's nobody's birthday. So I want you to notice this egg does not fit in the bottle or the flask. Okay, so light those candles for me. All right, so I'm not going to push this up. I'm just going to hold the bottom. Am I?
Oh my.
All right, now you should be able to explain what happened there. Thanks. Explain. All right, you should be able to explain.
That's magic. Some people like call it chemistry.
All right, and Manon's table, help me on here. Egg bottle, go. They're flying around, okay. Okay. Very good. And what did you say? It does what stick? What word did you use? Whoa, hold up. No pull in it in chemistry. What does the atmospheric pressure do? That's on the outside and you can't suck it in. It what? Pushes. It's just pushing the egg like crazy, and it pushes the egg in because this is higher pressure on the outside versus the teeny bit of a lower pressure system on the inside, and then it pushes it in until it comes to equilibrium once again. Because once it's open system again, all the pressures are the same inside and out. Okay, I'm glad I could entertain you with that. We've got two more things to talk about with pressure, and then we have a quick activity, and then we have some calculations today. This is called a barometer. Barometers are technically, well, they're used to measure atmospheric pressure. It's very difficult to see this, but there is a silver substance down here. Do you guys know what that silver substance would be? It's a liquid. Good, it's mercury. So literally what they used to do to measure atmospheric pressure, the atmospheric pressure would come into the sides here. It would be kind of equivalent on both sides. And there's Actually, mercury goes all the way over here. So essentially what they would do is they would allow the atmospheric pressure in. It's going to push any gas particles that are in here. And when it does that, it pushes the level of mercury to one specific level, let's say 740 millimeters. And they literally measure it in millimeters, like with a ruler. But this is like obviously got graduations on it, so they don't always have to whip out the ruler every time. So that's where we got the unit of millimeters of mercury from a barometer. So that's fun. Okay, it's cool. What we'll do in the lab, I want you to, now these are in-load drawings on Smartboard. It's not great. But I want you to draw this. This is a beaker. The bottom piece down here is a beaker. Okay. Can you guys tell what this thing here in the middle is? It's upside down. It's a what? Upside down graduate cylinder. Yep. We get fancy here. So we have a graduate cylinder. There's a little spout on it. It's upside down. And there's the base of it. What's a graduate cylinder got on the glass? Graduations, which is very helpful for us, right? So what we would do is we would fill the outside of the beaker with water. Make that blue for water. So there's water all down here. And there's water. I've got the whole entire graduate cylinder filled with water, all the way up. So at this point, the water has filled up all the graduation, so it looks like the volume is full. So what we would do is we would take some sort of substance or device that creates a gas. We hold our hand. I'm going to try to draw a little baby hand here. We put our hand underneath the water. We'd activate the device, whatever the device is, like a lighter, and the bubbles that come out of the gas, or that are formed from the gas, whatever the device is, would bubble up into our graduate cylinder. What should those bubbles do to the water? When you say push it out, you mean displace it? Yeah. Advanced terms. Okay, so it's going to displace the water, and as it displaces the water, where does the water go? Into the what? It should come into the beaker, right? So the bubbles might fill up the top space up there. Those are all bubbles. Once they've kind of settled, and the water would have been displaced by being pushed back into the beaker, then how would I measure the volume of gas I produced? Say again? What do you mean measure? Like, what would I be measuring with? Right, so maybe it was like 5 lines of graduations. Maybe that was like 5 milliliters a line. So 25 milliliters of the gas was produced. So we can use the graduation to share volume in a really fancy way. Okay? All right, so that's something we'll utilize in the lab probably Monday. I'm going to skip this one for a minute. These are all the same. Okay, so we're going to do a quick activity together, and I'm going to let you guys select your groups. I think groups of 3 will work for us. Choose them now with your eyes. Can you make a little eye movement? Okay. And meet me in the back. Go. You need goggles. You need goggles.
This last section looks like it's read over the instructions and right here. Sometimes, I think you're good to go. I might have rewritten one person or two, but read instructions on the first part of the activity. You have your hot temperature device. You do need to get a beaker and so forth. Follow those instructions to the T. Don't mess up. Will you guys come over here? Actually, go to that table over there. They only have 2. And then Drop in here, so a small station.
I want to make sure.
If you do not have a large beaker, there should be some back here.
Check for a beaker.
Here's how my husband, 3, 2, 1. Raise your hand if you have a 400 ml beaker or larger. 400 or larger. I think the 400 will be fine. Except this one. That's too big. That's not I can't. So I do need you to put like 8 milliliters, like this amount of the water into the aluminum can. Once you have it on the hot plate, then you turn it on. Do not pop it on the plate. Ready? Hold on. Please remember, I'm still talking. Second, we do need some ice and you need water, but really you only need 1 ice bath per big table. So one if you guys have a beaker, you're fine. Okay? Move on. Thank you. Put 8 to try right there. Alright, I'm gonna have you guys watch over here, because I think you're in the waiting phase. Am I right? You're waiting for vapors. Okay. So essentially, all you're going to do is whenever you start, like, let me help you just see the vapors. But you'll hear it boiling. It's like pop, pop, pop. You'll hear those little hits. I know you can hear it, which means it's starting to boil. And then let's go ahead and put it to 10. Can you bring up to 10? You're going to boil pretty like yesterday. Okay, so all you're going to do is whenever you see the vapors and you're like, Emily, give me some up, you're going to grab it with your beaker tongs and you're just going to invert your wrist so the top open to the can goes into the ice bath. Maybe about halfway. It doesn't need to be fully submerged, but you'll obviously see the indication of the reaction is done. Okay? So maybe just listen for a minute, watch for vapors for a minute, we'll probably close. If you put a ton of water in there, you'll be here all day. If you put a milliliter of water in there, you're only fine.
Slowly just like it was fine. As much as I could. I don't know what. It's not very clean, but no, we also
I'll give you the freedom to choose when you're ready.
Oh my gosh,
So I would suggest you let it vapor for like a minute because that means it's going to be better, but I'm giving you the freedom. I'm giving you the freedom. You got 2 trials, so here you Alright, hot plates off in 5, hot plates off in 4, hot plates off in 3, 2, hot plates off in 1. Okay. So, we're done with that one, but let me tell you how we're cleaning. Ice bath will go in the sink, like, pour it in the sink. Aluminum cans will be recycled. And then you guys can pick one of the next 3 activities to trial run now. I can only do the one that says vertical, I think it's the third one. I can do that later. So, go on to the next activity. If you have more hot plate, it's hot.
Alright, I'll take Yes.
Turn the hot plate off. Turn the hot plate off.
Just do the first one. I
Maybe like, let's go with golf ball. Let's do golf ball. I think we can do that one. There's going to be a short line at my station, so if you see a line, then hold off, because you can do something else while you wait. Or you can watch the way I'm basically
Wait, what's the next part? I'm gonna get it out.
I'm not blowing it up though. You guys are station.
Dang, it gets like non-stop. What did you do? I got it.
But I think I need hot Alright, so let's try this one. This is one of my favorite magic tricks. So all you're doing is literally putting about halfway full of water in your cup. You're putting your next one on top and getting a good feel with your palm. That good silly palm. Invert. And then don't be wuss. Take your hands out and see what happens. Okay? Try it out. Alright, you are done. Clean up your station. I'll see you back at your desk in 30 seconds. Throw the wet index card away. I do not want the wet index card back. Throw away the balloon. I don't want it. If you put your mouth on it, throw away the index card. Here's the marshmallow. Did you put the marshmallow in there? So let me say, take the marshmallow. Come back to your desk and do it, because I'm not. Alright, do not wrap the corn back around the hot plate. So let them kind of chill for a minute.
Woo! Well, that was fun, guys. That was fun. All right, if you have your goggles on still, you look cool and all, but I don't think you need them for now. We're doing notes. We are going to fill out pieces of our foldable. Have your foldable back out. Is Avogadro's Law one of your laws in your foldable? Okay, it's not. That's the only one that's not going to be in the foldable because we don't calculate with it a ton, but we definitely want to have the relationships established. So, in your lab, you experience some pressure, volume, temperature relationships, as well as amounts, which were moles. We're going to delineate those mathematically now. So Avogadro's Law can just go in your notes someplace. This piece will not be in your foldable. We're here together now, good? Okay, so Avogadro's Law, I'll tell you that the relationship is between moles, meaning amount, and volume. Okay, so you tell me, if I had a balloon, and I blew one breath into it, and then I blew another breath and another breath, what would happen? You use the right word here. The volume would increase, because what have I done to it? Put it in more amounts or more moles or more particles of that gas. So is this a direct or an indirect relationship? Right, because as one goes up, the other goes up. Moving in the same direction means direct. So what we're going to indicate this as is a direct relationship as it stands as a proportion. So N1, which is, what's N stand for? Amount or moles, right, specifically moles, over V1 equals N2 over V2. So what I like to say is this is scenario 1 when I write 1, this is scenario 2 when I write 2. So this is my example. One breath goes into the balloon, it blows up to a liter. One breath, 1 liter. If I put 2 breaths into the balloon, what would my new volume be? 2 liters. So literally you just solve for V2 using logic, but you could also do it mathematically with not so easy numbers. So this is the law, this is the math law, but what variables are staying constant? If you've noticed, I didn't mention some other variables, so which ones would be constant? So this is at constant temperature and pressure. There are only 4 variables we speak of, right? So if they're not changing, they must be constant. And you guys said this was a what kind of relationship? Direct. I saw like 4 people writing. I hope that you're feeling good about that. But I'm moving down a little bit, okay? So that's Avogadro's. Boyle's law. This is on your reading guide. What 2 variables are involved there? Pressure and volume. Good. Those are the 2 variables that are included. So you think about your box of air example. Think about the relationship between pressure and volume. And I want you to go like direct or indirect. You got 2 thumbs, direct or indirect. Use your thumbs. All right, most of us are saying indirect. Good, because increasing pressure squishes the volume down. That's an indirect relationship. So this is the direct relationship method. It looks like a proportion. The indirect mathematical relationship is more multiplication, not division. So P1, V1, so that's P1 times V1 is equal to P2 times V2. That's the V. V2. So this is Boyle's law. It's the relationship between pressure and volume of a gas. This is this piece can go in your foldable, right? Because this is the second page, first page. So make sure you're with me on some of those, okay? That way you're not doing double work. This is at constant what? Say again? Temperature and? So I'll put in there just for variable sake. Okay, so notice that the variables are included. The ones that are excluded will be considered constant because then we got too many variables going on. We can't really tell what's going to happen. And you guys said, is this direct or indirect? Indirect. What's another way to say indirect relationship? Inverse relationship. Good. Okay, moving down. This one's what page is in the book? Second or technically third? Okay. So Charles' law, based on your reading guide, what's the relation or what are the variables involved? Good. Volume and temperature. Okay. I'd like to say Charles went to Virginia Tech. So you remember that he went to Virginia Tech and those are VT, Virginia Tech. You'll appreciate it. Okay. So as Don mentioned with the temperature aspect of this guy here, what if I increase the temperature of a gas? What do they start to do, guys? Their kinetic energy is just going crazy. They're speeding up. They're speeding up. They're speeding up. As gas particles speed up, what do they naturally kind of do? When you say they expand, what are you trying to say? When they expand the volume of their individual particles. They're basically not individual, their overall surface area, their area they take up. So if I increase temperature, this is kind of our thought process, that increases the kinetic energy. They spread out. And when they do that, what happens? When they spread out, what variable is changing? So the volume is what? Increasing. So as you increase temperature overall, what happens to volume? So is this a direct or an indirect relationship? Direct. Okay. So the law for that, though, the equation, is that going to be similar to the first one or the second one set up? Because the direct relationships are proportions. They are like division. So that's V1 over T1 equals V2 over T2 at constant what? I get somebody other than this table up here. Kendall's back table. First table. Say again? What was the first one? Okay, N and pressure, the other variable that's not included. Okay, big star on this one though. We are talking temperature in what unit? You have to use Kelvin. If you don't use Kelvin, the proportionality will not work out. Because Kelvin is not a multiple of Celsius, it's a what? So it's not like a multiple, so it's not multiplied to get between Celsius and Kelvin. What do? We add. So since this is all like division and multiplication, if I have something that's a summation, like a variable like temperature, it will not work out with a proportional nature. So we have to be in Kelvin when we calculate that. right, Gay-Lussac, look at your folder, or was this one you were reading, Ed?
Yes.
Okay, so far we've compared pressure and volume, and we've compared temperature and volume, we've compared amount and volume. Okay, so what's another relationship we can maybe come up with? Okay, pressure and temperature. So this is also relating back to the egg example. If you heated these gas particles up inside and they started speeding up, what do they do with the walls of the container? If the particles speed up, what do they do with the walls of this container? They bounce off like more or less? Way more, right? So if they're speeding up, they're moving fast, they're hitting the walls of the container. The definition of pressure is what? This was on the notes you took from warm up. Pressure is okay. So caused by collisions of gas particles or collisions with the container wall. So if I heat these up, I speed these up, they collide with the container wall more. So you guys are saying increase. Hold on. What did I increase to cause it? Good. Increased temperature increases kinetic energy. Increases collisions with the container wall. This is our logic for like full understanding of what the variable relationships are, okay? And when I do that, what is affected? Like what's going to change? Increase the what? The pressure. So as temperature increases, it eventually will cause a pressure increase, but there's a lot of stuff happening in between that. So this is a what? A direct or an indirect relationship? Direct. And therefore, how would this one be written? Proportion or multiplication? Proportion, good. So we're going to do P1 over T1 equals P2 over T2. And this is at what? Constant amount and volume, good. And again, we have temperature, so what do you have to write down? Kelvin. Make sure you're in Kelvin from Celsius. Okay, I want you to write down the combined gas law, which will be combining Gay-Lussac's, Charles's, and Boyle's. Look back at those three. Gay-Lussac's, Charles, and Boyle's. Look on your folder, that way you can see what you need to write it yourself, which you can read it. So it's combining what three variables, guys? Pressure, volume, and temperature. How are pressure and volume related? Pressure and volume.
Indirect.
This is the only one that's indirect, because as you increase pressure, like on a box of air, the volume would decrease. So how do I have put pressure and volume in a relationship, like on a mathematical relationship? Next to each other or over each other? Next to each other. That's the one that as one goes up, one goes down, so they have to be multiplied by each other. So P and V will go together, so I'll call this P1 and V1, equals P2 and V2. Whose law is this? Boyle's law, right? Okay, how are pressure and temperature related? So they're direct, so we're dividing them, right? So if I just put pressure here, it's already there, right? So where am I putting temperature? Okay, so this is T1, this is T2. So this here represents whose law? Gay-Lussac's, right? And whose law do I actually already have here? I didn't write it myself, but it's there. What's Charles's law? Good. V over T is equal to V over T. So I actually have three laws combined in one. Boyle's was the first one. PV equals PV. And then we had Gay-Lussac's, and then we had Charles's. But in the end, we would just call that combined gas law, knowing that they're all relationships have been displayed appropriately. But this is at constant what? Amount. Because once we change the amount, we start to screw up all kinds of things. Pressure, volume, maybe not the temperature, but we do start to affect many variables. All right, that one will not have a direct proportionality or indirect because it's got multiple variables involved. Give me a thumbs up when you're good with combined. Okay, so pull up the lecture notes I gave you. It had the phase diagrams and first on it. On the back side of it has gas stuff, so that's what we're starting together. It's on the back of that, yep. Alrighty, so essentially now that we know the logic, like the background of how variables are related, we know the mathematical relationships, we're going to apply the mathematical relationships. So I'm going to demonstrate how the work that would be required to problem solve appropriately with success, okay? Is this number 1 on your sheet? Verify, okay, good. So this is going to be 1 through 16. Notice for homework, do you see? What's for homework? 1 through 16. We're going to probably knock out half of them or more right now. So I would have this not on the little piece of paper, because it can only just do the 16 problems on this paper. Have this either in your notes or on a clean sheet so that you can label them perfectly.
Yep.
Read it again. Do the same thought. So lecture notes 1 through 16. You ready? Okay, I think you're ready. So here we go. What I'm looking for is a list of variables first. So when I read the problem, I need to see the variable, and I need to write down the letter variable it is. So when I see 700 millimeters mercury, what variable is that? Pressure. So that's the first one I'm going to see. So I'm going to put P1 and call that out as 700 millimeters of mercury. All right, so a 700 millimeter mercury sample of hydrogen has a volume, oh, I see another variable, a volume of 500 milliliters. So what am I going to call that? V1. And you'll notice that this scenario was provided together. So that's actually why I'm calling them both 1 and 1, because they were given together as a collective variable system. Okay, so now, if the pressure decreased, so this is our scenario 2. If the pressure decreased, P2 is what? Okay, 538 millimeters of mercury. So here's our question, what will the new volume be? So what am I looking for? V2. All right, Don is going to pass out calculators. Raise your hand if you need one. Just grab one from the tote. He's going to scurry across the room, so you got to be fast. He's not waiting on you, so you just get your hand in there. Okay, this is not the work side. This is just laying out the law. Okay. He's being nice. Beggars can be choosers. Alright, so after we write down the variables, I think this is really important to do. If you don't do it on your own and you kind of just label it up here in the problem like P1, V1, P2, and V2, like I get that you can go back to the problem and read, but when the problems get kind of longer, I think it's nice to write a list of variables out. So, step 1, variables. Step 2, figure out the law. Which law is this? Okay, so what's the formula for Boyle's law? I hear you. Okay. After we figure out the law, 3, solve for the question. So I want it, before I start plugging numbers in, what variable am I solving for again? I want to rearrange this to solve for V2. So when I want to do that, what do I do over here? So I'm essentially isolating V2 by dividing by P2. P2 cancels. So V2 has been isolated, yes? And that is going to be P1 times V1 over P2. Now I can plug this information in. What's P1? 700 millimeters of mercury. You have got to write the units, because if you don't, you won't notice when units are not matching, and you won't have the right ability. You won't have the ability to cancel units out. So there's P1. That's 700 milliliters of mercury. What else? What's V1? 500 milliliters. Okay, and I'm putting the dots here, decimals, because they're indicating a certain number of sig figs. I'm going to divide that by P2. Thanks, Corbin. What's P2? 538 millimeters of mercury. And you guys tell me what unit cancels here? Good. There's a millimeters of mercury on top. There's a millimeters of mercury on the bottom. What unit remains? Milliliters. Is that a good unit for our question? How, like, it's volume, right? What are the two units for volume we could use? Good. Milliliters or liters, as you wrote down in your notes earlier. So this is totally fine. Solve. Sorry guys, I'm special. On the regular. Alright, do we have an answer? 651 milliliters. How many sig figs should be recorded?
3.
Good. This one has 3, this one has 3, this one has 3. We're good to go. And we have volume, V2. Alright, so you're going to say, okay, I think I can do this in my head. I know I can do this in the calculator, but I can't see that. So minimum, what I'm looking for, minimum is this right here. Okay? Because I get you can label this in the word problem itself, and I get that you can rearrange the formula. Once you've done it 5 times, you're going to do it 1,000,000 times. But once you've done it a couple times, you can do that. Minimum, I want to see the work, especially seeing the units so I can type and cancel. Okay, take a minute to solve number 2. I basically am just showing you what I think you could do to be successful every single time, but I know that some of you guys will work a little differently. So far, number 2, what did you guys find to be the important information? At 8 a.m., a sample of potassium chloride decomposes to yield a solid and 50 milliliters of a gas at 720 millimeters of mercury. What's important there? I hear 50 milliliters of a gas. Okay, I'm going to call that B. What else is important?
720 milliliters.
Okay, good. So that's going to be a pressure because I'm identifying that unit of pressure as a pressure. At 5 p.m., the volume is changed to 53 milliliters. What was the atmospheric pressure at 5 p.m.? What else is important?
53 milliliters.
Good, 53 milliliters. That's a volume because milliliters is a volume unit. And what's our question?
Pressure.
The second pressure. So since these first 2 were given together, I will call those 1s and 1s. And then the second scenario would be the 2s. And lastly, this is kind of a review question. You guys can do that at the end. So I'm just helping you dumb down the word problems to be an approachable problem. If you are good to go, I think you should try one of each section. You'll notice it says boiled and pearl and baby cells. So take some time in your script right now, especially to try to process one of each section. Alright, don't go to 3. I want you to go down to 6 if you're done with 2. That way you can try and look from each of the sections. So either leave some space or you just mix up the numbers, that's fine. I want to just make sure you know how to isolate a denominator. So I's up here in 3, 2, 1. Some of you guys are very math savvy, but do you guys know what cross multiply and divide is? Or it's also known as, I don't know, copy dot floppy, something like that. Bow tie method, I don't know, butterfly method. There's all kinds of names for it. But if you were to divide, or sorry, I know we're solving for B2 here, but if you had to solve for T2, I would think it would be best to multiply and divide versus trying to rearrange stuff on the spot. So when you cross multiply, you cross multiply the two variables that are top and bottom to each other. So that's then going to say V1 times T2. And then you set that equal to the other cross multiply, which is the other side of the x. So you're going to set that equal to V2 times T1. And so once you cross multiply, you can isolate any of these variables very easily. So if I wanted to isolate T2, which is not what question 6 is asking, but if I wanted to isolate T2, it would be very easy because then I would just divide by V1. So cross multiply and divide. If you get stuck and you don't know how to do it, let me know. Okay, it's been a while for some of you since like what, algebra 1, whenever that was. So cross multiply and divide. All right, so I think you're good to go. I'm gonna let you guys keep flowing through different questions. I would try a couple different from each side of the each section of the sheet.